example, look at how we can calculate the probability that a randomly graduate passes the bar exam. Did all write the answer for this question when I was writing here? Right, hopefully. Then the next one. This also we will look at how we can do this one. Suppose we are interested in the condition of a machine that produces a particular item. From the experience, it's known that the machine is in good conditions 90% of the time. When in good conditions, the machine produces a defective item 1% of the time. When in bad conditions, the machine produces a defective 10% of the time. An item selected at random from the current production run was found defective. What is the probability that the machine is in good condition? This is also, they are asking to calculate the conditional probability. But here also, more than one activity, it is depending on calculating the probability. So here also, using the tree diagram is easy to calculate the probability, right? So now we will look at how we can. The machine may be in good condition or in the bad condition, right? So first, the machine status. Good, this is bad. If it's the probability for being a good condition, 90%. And the probability of being the machine in the bad condition, 0.1. Then producing the defective items, according to this problem, producing the defective items depending on the condition of the machine, right? So when the machine is in the good condition, it produces the defective items and non-defective items, right? So according to this, when in good condition, the machine produces a defective item 1% of the time. So that is 0.01 defectives it will produce. When the machine is when the machine is in good, so the non-defective is 0.99. Right? So similarly, when the machine is in the bad condition, here also two possibilities. It is defective and it is non-defective. When it's a bad condition, it produces 10% of the time, so 0.1. So non-defective 0.9. So this probability actually means conditional probability, that is probability producing defective items given that machine is in the good condition. So here, similarly for each and every one, you can get the idea of the conditional probability. So then the final, at the end of the branches, we can calculate the joint probability. Right. So the first branch, machine is in the good condition and produce defective. that is equal to 0.9 into 0.01. Then it is machine is in good condition and non-defective. That is D complement, right? Non-defective. That is 0.9 into 0.99. Then it is the machine is bad and producing a defective item. So that is 0.1 into 0.1. It is machine is in the bad condition but producing non-defective item. The complement. So that is 0.1 into 0.9. Now, what is the probability that the machine is here? Start with this an item selected at random from the current production run was found defective. If the selected item is defective, what is the probability that the machine is in good condition? So we have to find the probability. If the machine is in good condition, if the selected item is defective. This one we have to calculate, right? If the selected item is defective, what is the probability that the machine is in good condition? The conditional probability they ask. So according to the definition of conditional probability, this can be calculated probability of G intersection D divided by probability of D. Then probability of G intersection D. That means machine is in good condition and the produced item is defective. That is given by this probability. That is 0.9 into 0.01 divided by if the item being defective. So item being defective, there are two cases. This is also produced defective item. This is also produced defective item. Right? So the good condition machine producing defective item or bad condition machine producing the defective item. So that the two probabilities we have to add. So producing defective items 0.9 into 0.01 plus 0.1 into 0.1. This one plus this one. Right? I think when you are simplifying this one, that is 0.4737. That is 47.37 plus. This is the probability you can get. Right? So this is the learn how we can use tree diagram to calculate the probabilities, right? And these are the exercises I am leaving as a homework, then you practice it, right? But the points we learned in the previous slides, by using those knowledge, then you can apply those knowledge to calculate these probabilities, right? So these are the some of the exercises we extracted from the past question papers, and then you practice it. Now we ending the basic probability. Now we will move to the next section. Is my slides visible? Discrete probability distribution?
Yes, ma'am.
Right. Okay. So now we move to the next session. These distributions are very important for making some hypothesis testing and estimations, right? So this chapter is a very basic foundation chapters for the statistical inference. Little later, we are going to learn the estimation procedures and the hypothesis testing procedures, right? And what are the probabilities we learned in the previous session? That is the that understanding we need to understand these probability distributions, right? Okay. Right. These are the learning outcomes. Define the terms random variable and probability distribution. At the end of the session, you will be able to define what is the random variable and what is probability distribution. You will be able to distinguish between discrete and continuous probability distribution. You will be able to calculate mean, variance, and standard deviation of a discrete probability distribution. You will be able to describe the characteristics and compute probabilities using the binomial probability distribution. You will be able to describe the characteristics of and compute probabilities using the Poisson distribution. Apply the binomial and Poisson distribution to solve business problems, right? These are the learning outcomes we are expected from you. Right. Now we will introduce a concept, random variable, right? So random variable, already we know that variable, right? What is a variable? Variable, it will take different values. It will take different values. Then we are saying that it's a variable. For example, marks of a student. So there are possibilities of the marks are from 0 to 100. There are possibilities, right? Then sales of a company for last 10 years. The sales of a company for last 10 years. So there are different figures we will get. So sales is a variable, right? So similarly, this random variable also a variable. It will only assume numerical values. But in the variable, it may assume in the normal variable when we are defining gender of student, right? Here, male or female, it takes different values, right? Then highest education qualification of an employee, highest educational qualification of an employee. It also takes various values. So the variable may take numerical value or non-numerical value, but random variable always takes numerical values, right? But these numerical values are associated with the random outcomes of an experiment. Already we learned the random experiment, and the random experiment results some outcomes. From those outcomes, we have to take the numerical values. Those numerical values associated with the variable is called a random variable. So here, where one and only one numerical value is assigned to each sample point, right? So what is a random variable? Is a variable that assumes numerical values associated with the random outcomes of an experiment, where one and only one numerical value is assigned to each sample point. Because here the numerical value of a random variable is determined by the outcome from a random experiment. So this value also is determined by chance. That's we are saying that random. The value for this variable, if determined by a chance or by the likelihood, that is called a random variable. For simple example here we will take to understand what is a random variable. Our experiment tossing a coin. the random experiment, right? Here we are saying that this random experiment, tossing a coin. Tossing a coin twice, right? So from this experiment, what are the possible outcomes we can get? There are your sample spaces. There are 4 possible outcomes are there. Both times you can get heads, or first time head and the second time tail, or first time tail and the second time head, or both time tails. These are the possible outcomes for the random experiment. And also we know that probability of hitting 2 times heads, or probability of hitting head and tail, or probability for getting tail and head, or probability of getting 2 tails. Both are equally likely occurred, so 1/4 for each and every outcome. The chance is 1/4 because 4 outcomes have equally likely. So based on the classical approach, we have 1/4. Now we are defining a variable x such that number of heads when tossing a coin 2 times. When tossing a coin 2 times. So now anyone, can you tell what are the possible values for x? Anyone? Now we are defining x is number of heads when tossing a coin 2 times. Number of heads turn up or turn when tossing a coin 2 times. What are the possible values for x? Any student? If both times we got heads, then how many heads are here? Please unmute your mic and tell the answer. Now we are tossing a coin 2 times and we got H8. So in this outcome, how many heads are here?
2.
Huh? How many heads are here? 2, right? H, 2 heads are there. So from this outcome, we can get 2 heads. From this outcome, how many heads we have?
1.
1. From this outcome?
1.
1.
So 1 is also possible. From this outcomes, how many heads are here?
No.
0, right? There is no heads, 0. So here, what are the possible values for x? 0, 1, 2. These values are determined by the occurrence of these outcomes, right? These values are determined by occurrence of these outcomes. So now this variable is called a random variable, right? So now here you look at a random variable is a numerical measure of the outcome from a random experiment. So it is a numerical measure. It measures the number of hits we got when tossing a coin twice. Right? So these values, these numerical values are determined by the outcomes from the random experiment. Right? This number of hits when tossing a coin twice is a random variable. Similarly, the number of tails when we are tossing a coin 2 times, right? So similarly, this is a very simple user-friendly example to understand the random variable. So random variable is a variable, but its values of these variables are determined by the outcomes of the random experiment. That's why we call this is a random variable, right? So this understanding you need, right? Usually, these random variables are denoted by using the letters capital X, capital Y, right? Right. For examples, number of defectives in a production line, right? Suppose, for example, here we are taking X, denoting X as in a production line. Right? Now say that there are 100 items in a production line. The particular production line, it produces 100 items. So now what are the possible values for X? Can anyone tell what are the possible values for X? If it's producing 100 items in a particular line and X denotes the number of defectives, then what are the possible values for X? If all items are non-defective, then what is the value for X?
0, ma'am.
0, right? If only there is one defective out of 100, then X equals
99.
one defective. If only one defective, because X denotes the number of defectives. If there is only one defective, then X is 1. If there is only 2 defectives, then X is 2. Similarly, if all the items are defectives, then it is 100. So, these are the values taken by X. X equals 0, 1, 2, up to 100. Right? Then number of customers waiting for a service at a banking counter for a half an hour period. Right? So this is also if there is a particular lunch hour, how many number of customers waiting for a service during the lunch hour time. If there is no customers, 0. If there is one customer, 1. So similarly, it will go on. Right? Then assembly time of a certain product, X. So it takes take the minimum time 1 minute and maximum time 5 minutes, say, right? To assemble a particular product, the assembly time may change in between 1 to 5 minutes. So here X takes infinite number of times because now here this is our time period. 1, 2, 5. Within each and every point is possible, right? In this interval, each and every point is possible to assemble the product. So here infinite number of values taken by X. So here how we are taking the values? 1 less than or equal to X, less than or equal to 5, right? Within any point, X will take. But here we can write X equals 0, 1, 2, 200. Right? So the lifetime of a certain electrical bulb. Right? Here also we say that 10 hours to 100 hours. So if lifetime or 0 to 100 hours. 0 less than X less than or maximum 100. So 0 to 100. So any point is possible. 0 to 100. So here also infinite number of points are possible. Within this interval, any value is possible. So here these two are infinite number of values possible. For others, countable number. Here we cannot count how many points are there. But in these cases, we can count. Here, 101 points are there. Right? So all these are examples for the random variables. Right? Now, the random variables can be divided into two cases. One is a discrete random variable and other one is a continuous random variable. So what is how we can distinguish the discrete random variable from the continuous random variable? This random variable can assume a countable number. or finite values. It will take finite number of values. This is called the discrete. But here we say that we can mark in the number line as a points, right? So tossing, when we are the number of heads, when 2 points are tossed, there are 3 possible values, 0, 1, 2. So that is a discrete random variable. Number of defectives out of 100 items. There are also 101 possible values are there, 0 to 100. All are integers, right? So this is called the discrete random variable. So the discrete random variables can assume a countable. We can count or finite, infinite values also it will take, but it is countable. We can count 0, 1, 2, 3. In such manner we can count. So it is called a discrete random variable. Right? The values of a discrete random variable can be plotted on a number line with spaces between each point. Right? In between 0 to 1, no point it will take. 0 it will take, 1 it will take. In between 0 to 1, no point it will take. Similarly, 1 it will take, 2 it will take, but in between 1 and 2, no point it will take. In such manner, you are having the values for the random variable that is called a discrete random variable. So these are some examples for discrete random variables. First one is a experiment. They are making a salesman making 100 sales calls, and for this experiment we are defining number of sales, right? So maybe if there is no sales out of 100 sales calls, it will be 0. And out of 100 calls, only 1 sale occur, then X will be 1. Out of 100 calls, 2 sales occur, then it will be 2. Out of 100 calls, all the 100 sales occurred, then it will take 100. So this is a countable values, 1, 2, 3. So for finite number of values, it is a discrete random variable. Similarly, other 3 examples also for the discrete random variable, right? But here you look at, here this is a finite numbers. This random variable has only finite numbers. Here 101 values, here 71 values, here 34 values are there. But in this case, now we look at we are counting the car at 12 between 11 to 1. Right? It is an imaginary example. Anyway, cars arriving between the 11 and 1. We are putting it as a 0, 1, 2 up to infinite. We don't know the maximum number, right? How many cars, maximum, how many cars will arrive during this interval at the 12, we don't know. So if we don't know the maximum number, then the maximum number we will denote it by infinity. The maximum number of cars arriving during the time period 11 to 1 at a particular 12. If we don't know the maximum, then we will denote it by infinity. So in this case, these numbers are countable. We can count 0 cars, 1 cars, 2 cars, we can count, but we cannot say in a finite number. The maximum number we don't know. So in this case, infinite number of values are there, but it's a counter, right? Now we are coming in another part, continuous random variable. This continuous random variable can assume values corresponding to any of the points contained in one or more intervals. That is, values that are infinite and uncountable. If these 2 cases are satisfied, it should be infinite and uncountable, then it is called a continuous random variable. If we are taking the time 0 to 4. Here, all values, each and every point is possible. So here we cannot count 1, 2, 3, 4. We can't count because there are infinite number of points within this interval is there. So such case is called if that is the case, then the random variable is called the continuous random variable. Right? So the values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So here, all these points are filled. So there is no uninterruption between 0 to 4. Right? For example, the weight, we are weighing 100 people. We are looking at the weight of 100 people. So the variable we are defining weight of a student, right? Or weight of an employee. So it may be 45.7, 45.02, 45.78, 78, 78.92. Similarly, there are possible, infinite number of possible values are there. Similarly, measures of lifetime. We are measuring the lifetime of a battery. Random variable, here also lifetime. In measuring in hours, lifetime. It is also 900, 900.001, 912.85, right? So this is also, there are infinite number of possible values are there. Such kind of variables are continuous random variables. Amount spent on food. Right? We are measuring the time between two arrivals. Right? All these are continuous random variables. So simply how we can differentiate the discrete random variable and the continuous random variable. For the discrete random variable, the values we are getting by counting. Right? Number of customers, we are counting. Right? Number of defectives, we are counting. Number of heads when tossing a coin, we are counting. Right? So that is a discrete random variable. But in the continuous random variable, we are measuring, not counting. We are measuring, right? Weight of a student or lifetime of a battery, right? Amount spent on food. The time between two arrivals. All these are not counting. We are getting the values by measuring. So if the values are getting by measuring, that is a continuous random variable. The values of the random variable we are getting by counting, then that is called a discrete random variable. This is an idea, a clue you can use to distinguish the continuous and the discrete random variable. Right? Right. Now your part, right? So the first case. Right. You have to identify whether the random variable is a discrete or continuous. X is a random variable that represents the number of shares of stock in the Dow Jones Industrial Average that have price increases on a given day. Right. Now read this statement and tell me whether it is a discrete or continuous. Unmute your mic and tell it. Huh? Now, based on the simple definitions for the discrete and continuous, now tell whether it is a discrete or continuous. What is the first thing you have to look at? Whether we are measuring or we are counting. Based on that one, you can decide. Right. Now, based on this idea, can you identify whether it is a discrete or continuous? Are we counting or are we measuring here in this case?
Counting.
We are counting. So because here we say that number of shares. So 0 shares that have price increases, right? So it may be 0 shares or 1 share or 2 shares. So here we are counting. So what is this variable? Is it discrete or continuous? Is it discrete or continuous?
Discrete.
Discrete, right. Second case? X represents the volume of bottled water in a 32-ounce container. First, look at whether counting or measuring. Is it counting or measuring?
Measuring.
Measuring. We are taking the volumes, right? Volume should be measured. So as it is measured, this is a continuous variable. Third one?
Continuous.
Continuous. Here also we are measuring the time, length of time, right? So it is continuous. Fourth one?
Discrete.
Discrete, right? Because we are taking the counting the number of home runs hit during a baseball game. So similarly, you can identify it is a discrete or continuous. This is, we will take it as exercise. Right. So now I am stopping this one. Tomorrow we will start with the probability. So tomorrow, because usually we have a power cut at 4 to 6. 3:15 to 5:20 or 5:15. So shall we start tomorrow evening 5 o'clock, 5 to 7? Is it okay to all of you?
Okay, ma'am.
Okay? Okay, right. So tomorrow we will have the lectures at 5 o'clock, evening 5. Right. So now I'm going to end my meeting, right?